All right, let's take a look at problem 7. So problem 7 is going to involve computing residual enthalpy and entropy using our SRK equation of state. And so for that, you can just use the MATLAB code which you used in the previous problem. And then also it'll require playing around with reference states. Okay. So let's read it, and then let's set up some preliminaries before we go through the specific problems. And so in this one, I won't do any number crunching, but hopefully just in setting it up, you'll be able to take care of that yourself. So use the SRK equation to calculate the following properties of isobutane: residual enthalpy and entropy at 10 bar 300 Kelvin, then enthalpy and entropy at 10 bar 300 Kelvin, using as a reference state saturated liquid at 1 bar. Then C, we're repeating, but using as a reference state hypothetical ideal gas state. And then D, the enthalpy and entropy of vaporization at 1 bar. Okay, so first, a couple of preliminaries to set this up. Okay, and so first thing would be computing. Okay, HR and SR. Okay, and so I'm not going to do this. So we computed SR or HR in the last problem, and using the MATLAB code, it should be pretty straightforward. Okay, but remember the general idea is we need to collect TC, PC, and omega from the appendix in the back of the book. And then if you also know the temperature and pressure, we can plug that into our SRK black box. And then out will come, of course, compressibility, molar volume, HR, and SR. Okay, so where computing Z and V, well, Z and V are required to be calculated first before you can calculate HR and SR. But you can also use those to identify which HR and SR to use if you obtain more than one real root. Or you remember, say that the enthalpy of your vapor phase is going to be larger than that of the liquid, so your largest or smallest residual enthalpy will be that of the liquid. Okay, but general idea being to get HR and SR using SR equation of state, I have my black box, my calculator, in which I input TC, PC, omega, along with my temperature and pressure, and out will come my residual enthalpy and entropy. Okay, and then the last thing to keep in mind is, actual property is residual plus ideal gas. Okay, so we get the complicated term from the SRK equation of state, which accounts for the fact that molecules interact and take up space. In terms of the ideal gas term, okay, remember that we showed, and there's a screencast for it too, the differential of enthalpy for an ideal gas is just Cp ideal gas dt. And so if you wanted to get, say, delta H, and going from some T naught, we'll just write it as, say, T naught to T1, okay, would just be integral from T naught to T1 Cp ideal gas dt. In terms of enthalpy, okay, the differential of the, or not enthalpy, differential of entropy for an ideal gas is Cp ideal gas over T dt minus R over P dP. Okay, so if I needed to calculate the change in entropy, okay, now here I said T naught to T1. Really, it's some state 0 to state 1 because enthalpy of an ideal gas is only a function of temperature. Entropy, though, is a function of temperature and pressure. So if I were likewise to say going from state 0 to 1, okay, state 0 is going to be at some T naught and P naught, okay, and then state 1 is going to be at some T1 and P1, okay. So delta S then, and going from some state 0 to state 1, would be integral of Cp ideal gas over T dt. That's an integral from T naught to T1, okay, minus integral of R over P dP, and that's just simple log ratio of pressures, but let me just write it as such for now. So that second term I can readily evaluate. And then this first term, okay, just like here, remember heat capacity of an ideal gas is only a function of temperature. And if you were to go to, so Appendix A in the back of the book is where you'd get TC, PC, and omega. If we were to go to Appendix B, you have ideal gas heat capacities, right? So the book provides us with polynomial expressions for heat capacity, and it's readily, easy enough to evaluate the integral of a polynomial. And even when you have 1 over t, the first term will be a naught over t, and then you just have a polynomial from there on out. Okay, so computing the integrals of CP can be done readily, and then the integral of r over p dp, no problem, right? Log ratio of p's. Okay, so that's kind of, and of course parameters would be available for your CP expression, just like TC, PC, and omega would be available for isobutane. Okay, and so just knowing that, so you can do the calculations. So when I say calculate residual enthalpy and entropy at a given condition, or if we need to calculate a difference in ideal gas values, you can do it. All right, and so that's why I say my focus is going to be on just kind of walking through the problems to try and figure out exactly what needs to be done. Okay. All right. So in problem A, okay, you're asked to calculate HR and SR at, and we're given a temperature and pressure, 10 bars, 300 Kelvin. Okay. Okay. So this one's pretty straightforward. You'd go to Appendix A. You would look up TC, PC, and omega. Once I have those along with temperature and pressure, I can plug into our MATLAB code and I can calculate HR and SR. Okay, it's a matter of, are we told what phase we have? No, but we are told that at, let's see, saturated liquid, so at 1 bar saturation is 266 Kelvin. So we're not exactly told what phase we have. Here pressure is increasing 9 bars, temperature is only increasing slightly. I would guess we have a liquid. Okay, but look, I overlooked something. The problem's even easier. We're told that the ideal gas constant pressure heat capacity could be taken to be constant and equal to 96.5 joules per mole Kelvin. Okay, so when it comes to our integrals of CP is just constant. All right, and so delta H just becomes CP delta T. All right, cool. Okay, and then here CP is constant. This becomes CP log T1 over T naught. Okay, and so you got it. So log ratio of temperatures. Okay, all right. So you could just plug into our MATLAB code and get HR and SR. Okay, so now it's for B. Okay, B is where we have to start to think through things. B says enthalpy and entropy at 10 bar, 300 Kelvin, and we're going to use as a reference state the saturated liquid at 1 bar and saturation temperature is 266 Kelvin. Okay, so we want H and S. Okay, I'm going to label this as H1 and S1. Okay, is our state of interest. And so that's at 10 bar, 300 Kelvin. Okay, and we're going to have a real reference state. Reference state of 266 Kelvin and 1 bar. Okay, and so remember, how you could think of a reference state is how we're going to define our zero. Okay, and so basically, H naught and S naught will be equal to 0 at 266 Kelvin and 1 bar. Okay. Okay, so our reference state is going to be our state 0. Our state of interest is state 1. Okay, and so basically how this would work is, if I want to compute, and let's just work with enthalpy, right? You'll see we'll get the same expression for entropy. But if I want to compute the enthalpy of my state of interest, H1, minus the enthalpy of my reference state, or my reference state H naught, okay, I could write that as, now I'm going to break up enthalpy. Remember, enthalpy or any property I can write as a sum of residual and ideal gas term. Okay, so I can take this and write this H1 minus H naught as H residual 1 minus H naught residual, okay, plus H1 ideal gas minus H naught ideal gas. All right, so essentially all I've done is H1 I can write as H1R plus H1 ideal gas. H naught I can write as H naught residual plus H naught ideal gas. Okay, and now I'm just collecting terms. Okay, and why I might do that, right, is, okay, so now I have H1 minus H naught is equal to H1 residual minus H naught residual. Okay, now, okay, in this case, right, this is going to be at some T1 and in theory P1, okay, and this would be at some T naught and P naught. Okay, I write this down for the entropy case. Enthalpy is only a function of T, and so what that's going to look like then is I come back up here to my preliminary and going from some state 0 to state 1, delta H is just integral from T naught to T1 Cp ideal gas dt. Okay, so this term is just equivalent to integral from T naught to T1, T naught to T1 Cp ideal gas dt. All right, where this problem we're even told that the heat capacity is constant, so it's just a Cp T1 minus T naught. Okay, but I'll leave it at that. Okay, so then rearranging over here, I'm going to take this and write this as H1 is equal to H1 residual minus H naught residual plus integral from T naught to T1 Cp ideal gas dt plus H naught. Okay, well, H naught, all right, is our reference state enthalpy, which is how we define our zero. Okay, so if I wanted to calculate H1, all right, H1 then would just be H1R minus H naught R plus integral of T naught to T1 Cp ideal gas dt. Okay, and that's it. Okay, so the idea being, I know the temperature and pressure of my reference state, so, and I know the temperature and pressure of my state of interest, so I can use our MATLAB code to readily calculate H1R and H0R. And then here, right, and we're told Cp is a constant. This is just Cp delta T. Okay, that's it. And if I wanted to do the same thing for entropy, right, it's going to be exactly the same. S1 would be S1R minus S0R. Okay, plus, now where things differ is, remember, this is T naught to T1 Cp ideal gas over T minus dt minus integral from P naught to P1 R over P dP. Okay, Cp again, we're told it's constant, so we just have a log ratio of T's and log ratio of P's. We've got to compute for those last two terms. Okay, cool. Okay, so the challenge is often just what's meant by this reference state. Okay. All right, so let me add another page and let's look at the next problem. Okay. So then if we look at C, okay, C says now we're going to take our reference state to be a hypothetical ideal gas at 1 bar and 266 Kelvin. Okay, so in B, our reference state was a real fluid at 1 bar and 266 Kelvin. Now we're going to be a hypothetical ideal gas at 1 bar, 266 Kelvin. Okay, and I'm going to go through the whole long-winded setup just for completeness, just for practice in terms of setting these things up, even though we could build directly off of B. Okay, so we want H1 again and S1 at 300 Kelvin, 1 bar. Okay, so reference state is an ideal gas. Oh, this is at 10 bar, I believe. at 266 Kelvin, okay, and 1 bar, okay. And I'm going to go, okay, by going through the same kind of thought process or same exercise. Let's set this up for enthalpy again, okay. So H1 minus H naught, okay. Remember, H I can write as a sum of a residual and ideal gas term. So this I can equivalently write as H1 residual minus H naught residual plus H1 ideal gas minus H naught ideal gas. Okay, so H1 minus H naught, okay, is equivalent to H1R minus H naught R. Okay, the change in enthalpy for an ideal gas is equivalent to integral from T naught to T1 Cp ideal gas dt. Okay, so enthalpy is only a function of T, and so this is just integral of Cp dt. Okay, cool. Going from some state 1 to some state naught. All right, so this is true in general. So how we work this for the case of an ideal gas or an ideal gas reference state is I'm going to again rearrange this as H1. Okay, and the magic trick I'm going to do might seem a little confusing at first, but key is I should be able to get to this point, right? Or actually, really the step above it, all right, and that should make sense. Okay, so then where we're going to go from this, and as an aside before we get there, okay, why I like this expression is if I know the temperature and pressure of my state of interest and reference state, I can readily calculate the residual contributions from our MATLAB calculator, and then this ideal gas term can readily be calculated. So in general, we have polynomial expressions for this. You can look at the back of your book. Or in this problem, we're told that Cp is just constant. But the key is this ideal gas term can readily be calculated. Okay. All right, so H1, okay, H1R minus H naught R plus integral from T naught to T1 Cp ideal gas dt. Okay, now plus H naught. Okay, so we're told that our reference state is going to be an ideal gas at 266 Kelvin 1 bar, which is at 8 knot. Okay, so one thing you could do, which would be a mistake, okay, what might be tempting is just to go to our original expression and say okay, H naught ideal gas is 0, and cross it out. Okay, now where that would be problematic is then I'm left with just H1 ideal gas there on the right hand side. All right, and what we're always interested in calculating are differences in quantities. Right? Remember, thermodynamics is a field of calculating differences. And so if I just said H1 ideal gas, I wouldn't know what to do with it. And so I'd end up with the same magic trick in terms of bringing H naught over. And so what the magic trick essentially is I'm going to take H naught here, and H naught can be written as the sum of residual and ideal gas terms. Okay, so I can rewrite this then as H1 is equal to H1 residual minus H naught residual plus integral from T naught to T1 Cp ideal gas dt plus this is H naught residual plus H naught ideal gas. Okay, so H naught residual, okay, those two terms cancel. H naught ideal gas is how I define my 0. Okay, cool. All right, and so now I'm just left with H1 is equal to H1R plus integral of T naught to T1 Cp ideal gas dt. Okay, cool. Okay, so it looks very similar to the expression for the last part, only here H naught R has been killed off. I said, thermo is a field of calculating differences. Remember, H1R is a difference, right? It's actual relative to that of an ideal gas. It's a difference in enthalpies. Okay, cool. Okay, and so, that's a trick. And, it follows if we were to do this for entropy. Okay, entropy, we would have S1 would be S1 residual plus Now it's just the ideal gas term is integral of T naught to T1, Cp ideal gas over R over T dt, okay, to T1, minus integral from P naught to P1, R over P dP, okay, and that would be entropy, okay. Cool. So it's just a matter of playing around with our reference states, okay. And if you find this confusing, I can tell you that in the past, plenty of students find these to be confusing, at least initially. Enthalpy and entropy of vaporization at 1 bar. Alright, enthalpy and entropy of vaporization at 1 bar. So what's going to be key here is if I have a system at two-phase coexistence, those two phases are going to be at the same temperature, pressure, and we haven't talked about chemical potential or empirical component states, molar Gibbs free energy. So just remember they're going to be the same temperature and pressure. Okay. So what do we need? So if you go down to D then, okay, D, if we start with delta H of vaporization, okay, delta H of vaporization is going to be equal to the enthalpy of my vapor phase minus the enthalpy of my liquid phase. Okay. Now let's break this up again. Let's write where you remember enthalpy can be written as a sum of a residual and ideal gas term. Okay, so this will be HV residual plus HV, and actually let's group it just like we did before. So this is equivalent to HV residual minus HL residual plus HV ideal gas minus HL ideal gas. Okay, so the key is if I have two-phase coexistence, if I have two phases in coexistence, they're going to be at the same temperature and pressure. Okay, well, enthalpy of an ideal gas is only a function of temperature. So if I have two phases at coexistence, the ideal gas contribution of their enthalpy is going to be exactly the same, right? This term will be 0 because these two enthalpies will be exactly the same. And so what I'm left with then is just delta H of vaporization is equal to HVR minus HLR. And so as long as you know the temperature and pressure, right, we already looked up TC, PC, and omega from Appendix A, I can calculate the enthalpy of my vapor and liquid and use that to calculate delta H of vaporization. Okay, cool. Okay, entropy of vaporization then we can get in two different ways. Okay, the first would be we could do the same direct route. So delta S of vaporization would be S vapor minus S liquid. And so that would be S vapor residual minus S liquid residual plus S vapor ideal gas minus S liquid ideal gas. Okay. Well, now entropy of an ideal gas is a function of temperature and pressure. Right. We have the equation. Where's my cursor? Well, right here. Come on, where's my, right here, right, if you can see my tiny little cursor. Alright, this is our ideal gas entropy, right? So we said ds is Cp over T dt minus R over P dP. Okay, but my two phases are at the same temperature and pressure, so the entropy of those, the ideal gas contribution of the entropy of those two phases are equal. Okay. So I'd get the delta S of vaporization is equal to SVR minus SLR. Okay, cool. And if you wanted to take it a step further, okay, the other way we could do this is remember G is equal to H minus TS. Therefore, delta G of vaporization is equal to delta H of vaporization minus T delta S of vaporization. Okay. Now, if I have two phases at coexistence, a pure component system, the two phases are at the same temperature, pressure, and they're also going to have the same molar Gibbs free energy. Okay, and so this is for our pure component system here. Delta G of vaporization is equal to 0, and so delta S of vaporization is equal to 1 over T delta H of vaporization, right? And so since you had just calculated delta H, you could just as well use this equation to calculate delta S. Okay, there you have it. Okay, and that takes us to the end of the problem statement. Yeah, so hopefully that gives you enough to be able to do it.